Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll go through the sample paper 2022 for this 9701 Cambridge International paper 1. So the examination format has changed in the sense that it's no longer 1 hour, it is now instead 1 hour 15 minutes. This is just a specimen paper. It's basically based on the new syllabus, which is not too different from the old ones, except that there is no more data booklet provided. The data booklet is actually inside the question paper itself, which means there are a lot more stuff which you cannot get from the data booklet directly anymore. There are still 40 questions, but there is no more section B. So of course, you're thinking that they can ask you section B type of question as well, but probably not 10th question exactly. In this first question, which molecule contains 8 bonding electrons? So 8 bonding electrons mean 4 covalent bonds, because in each one covalent bond you have 2 electrons that are bonding. If we draw the display formula by drawing this kind of bonds without drawing dot and cross, because you don't have much time in multiple choice question. So what we have there is like that. Sc3H6 is your propene. So carbon form 4 bond. I am just drawing all the hydrogens so that the carbon form 4 bond 1, 2, 3, and 4. On this carbon 1, 2, 3, and 4. On this carbon 1, 2, 3, and 4. And last but not least, we have ammonia with, of course, 1 lone pair on the nitrogen. We're looking for 4 covalent bonds around, well, actually in the whole molecule, because the question specifies in the whole molecule. So what do we have? We have 1, 2, 3, 4 covalent bonds. Pretty sure A is the correct answer there, because 2, 4, 6, and 8 electrons, they are involved in bonding. Here you have 2, 4, 6, 8, 10, 12. You have 6 covalent bonds. You have 12 bonding electrons. You have 2, 4, 6, 8, 10, 12, well, more than 8 essentially. Here you only have 2, 4, and 6. You only have 6 bonding electrons, because these are 2 times non-bonding electrons. That is basically your lone pair, 1 lone pair of electrons there. In this second question, what do we have here? We have beams of charged particles in the presence of an electric field. So there's a deflection because they are charged. And the angle of deflection is proportional to the charge of a mass. So there is something to do with the charge, there's something to do with the mass. So first of all, this angle of plus 15 degree, so it's plus 15 degree, meaning to say compared to minus 5 degree, so greater deflection. So that means your angle is bigger. So angle is bigger due to one, bigger charge, perhaps, don't know, we are not sure, but also maybe heavier, lighter mass, because the heavier you are, the less deflected you are, because you are much more difficult to move. So you get deflected more because you are lighter mass. So this one, lighter mass there, must be for plus 15 degree there. So we're looking at relative mass and relative charge. So in terms of the composition of the particle, the bigger the angle, so we're looking at a greater total charge. So protons, each proton has a plus 1 charge, each neutron has 0 charge, each electron has a minus 1 charge from your IGCSE, GCSE, or O-level chemistry. So what are we thinking? We're thinking about 1 protons and 1 electrons there. So this is an atom. And then we have 3 protons and 5 electrons. So we have 2 extra electrons than protons. This is a minus 2 ion, because you have 2 extra electrons than protons. You have 3 extra protons than electrons. This is a plus 3 ion. You have 1 extra proton than electrons. This is a plus 1 ion. So what are we thinking? If we get deflected by this blah blah blah, so protons are deflected by plus 15. So proton is plus 1 charge, and they get deflected by plus 15. So if this is negative, so we're looking at particle Y being negatively charged. So particle Y must be negatively charged. Y is negative charge, or negative overall charge. So looking at all of these, we are really having only one where the particle Y has a negative 2 charge there, so it's going the other side. You have more electrons, so you are much lighter. It cannot be the atom, as this atom here will have no overall charge, so 0 over something will be no charge at all, so can't be A. So thinking about that, protons are deflected by angle plus 15. In another experiment, particle Y is deflected by angle of minus 5. So I'm really thinking about the minus 2 charge here. It is also heavier, so the heavier particles are the protons and neutrons. 3 and 3 are 6, 4 and 5 are 9. Looking at the masses, by right, the one that deflect less should be heavier, but then we really are looking at just the charges that should give us B as the only possible answer there, to be honest. Question number 3, this is to do with relative atomic mass calculations. So from your syllabus, you need to know that it's to do with the mass number. Mass number multiplied by the isotopic abundances plus the other mass number multiplied by the other isotopic abundances. And this is divided by the sum of the percentage. So 7.42 plus 92.58, that is naturally out of 100%. Make sure you use a square bracket so that, when you press calculator, you're not making some sort of silly mistakes, because silly mistakes will cost you some marks. And if you are in theory paper, structure paper, there will be no correct option to choose from. So be very careful. So that's my exact answer, but they wanted to 3 significant figures. So significant figure are counted from the front, 1, 2, and 3. So we look at the fourth one, which is 5 or greater. So to 3 significant figure, this will be 6.93. To 3 significant figure, as this is 5 or greater, we add 1 more there. Question number 4, different forms of the same element. Different forms of the same element, they are called allotropes. So there's the Buckminster fullerene, which is a C60 simple covalent molecule, as stated in the syllabus. So simple covalent structure there. Whereas diamond and graphite, your case study from previous 14 to 16 years old chemistry, these are giant covalent structure or giant molecular structure, of which you need to know how to sketch them, obviously. What is correct for all 3 substances? Bond angles of 120 are present. Well, if I just think about diamond and graphite, I can be thinking about graphite like this, diamond like this, where each carbon is bonded to 3 other carbon. You get a tetrahedral framework in this diamond. So even without talking about Buckminster fullerene, I just talk about graphite and diamond. So we know about this hexagonal ring structure where each carbon is bonded to 3 other carbon like that. So naturally you will get 3 bond pair and 0 lone pair. There's 120-degree trigonal planar. I haven't shown you the whole plane in this hexagonal structure, the layer structure of graphite, but very clearly the bond angles of 120 degree are present is not true for the tetrahedral diamond. So diamond, all of them are 109.5 degree carbon sp3 hybridized center. You're looking for correct for all 3, so A is already wrong. Delocalized electrons are present, not for diamond. I mean, diamond does not conduct electricity, right? So, B must be wrong. Giant molecular crystalline structures are present, not for C60, which I just mentioned, simple covalent structure. Which means D must be correct because all of them has sigma bond. You have carbon-carbon sigma bond. In between, you have double bond and single bond, but you definitely have carbon-carbon sigma bond, carbon-carbon sigma single bond, and that is present in all 3 substances here. Question 5, we have a total surface area of 150 cm square for this metal, and you coat it with silver by electrolysis, so you get Ag++ electrons depositing silver at the cathode. So this increase there is the increase in mass of the cathode, as you know from electrolysis, O-level, IGCSE level, GCSE level chemistry. So this increase in mass is the mass of silver deposited. If you have the mass of silver, you want the atoms of silver, we need to think about, and this is per cm square, so we have to relate to that. Well, first of all, find the mole of silver atom. the mole of silver is going to be mass over AR. So of course, you don't have a periodic table now. Your periodic table will no longer be in the data booklet. So I'm just going to show you the data, well, not the data booklet, the periodic table is at the end of the question. The screen is not the right way around. So let me just rotate this. And then silver is Ag has got a relative atomic mass of 107.9. You will see that these are the data, the constants and stuff. This is the infrared question, which will come to later on. And I forgot what value I was supposed to read already. Silver 107.9, 107.9. Pardon the screen flickering, 107.9. So that is the mole. So we know that the number of silver atom is related to the mole of silver multiplied by Avogadro constant. So it's 0.216 over 10. Well, actually, not yet, because they want the atoms of silver per cm square. So divided by cm square. So I'm going to divide that straight away by the area in cm square. So what do I need? I need 0.216 over 107.9 multiplied by 6.02 times 10 to the 23, which you can get from the data booklet at the end of this paper. I showed you just a bit earlier, and you got 150 cm square. You've got the number of atoms there because you already related the number of mole from the mass over AR. So 0.216 divided by 107.9 multiplied by 6.02 times 10 to the 23 divided by 150. My calculator show me 8.03 times 10 to the 18. This is atoms per cm square. Follow the math and you should get 8.0 times 10 to the 18. There is option A there. Question number 6, we're talking about the first ionization energy. So nitrogen, which is 1s2, 2s2, 2p3. So it's a group 15 element. And then oxygen is 1s2, 2s2, 2p4. So it's a group 16 element. We are really talking about the paired electrons will repel more than unpaired electrons. So this one here, the paired electrons in the same orbital will repel more than these unpaired electrons. So which one explains that there's a slight drop in first ionization energy from here to here, slightly easier to remove because you're removing this unfavorable repulsion between paired electrons compared to the repulsion between unpaired electrons. Option C must be the only answer there. Question 7, you're looking for largest overall dipole moment. So you're looking for the most polar. So just be aware that dipoles are vectors. Vectors, as you know it from physics, from mechanics and mathematics, is to do with direction as well as magnitude. So we know that oxygen is electron negative. We know that CH3 is electron donating by inductive effect, and there's more of these in the AS organic chemistry under alkene syllabus, inductive effect like that. So the overall net effect is like that. And you have a net effect of that and that. So no electronegative groups though. So it's not a big pool at all. And as you know, hydrocarbon compound containing carbon and hydrogen are considered non-polar. So even though I put down the arrow like that, but usually we consider hydrocarbon, petroleum products, that kind of stuff, non-polar. Well, do not mix with water. Here you got chlorine, which is electronegative on its own, and they're pulling in that direction. But you got oxygen, which is much more electronegative. So you get a bit of net cancellation. This one in the opposite direction than this one. So here, D is going to be non-polar as well, in the sense that these and these are 180 degrees. They are not bound to the same carbon, but they have the same magnitude in the opposite directions, 180 degrees to each other. The vector will cancel each other out. This and this will cancel each other out. This is also non-polar. You get a bit of cancellation, so compare C and B. B is the most polar, the largest overall dipole moment there. Question 8, we have combustions of alkanes. We know that alkane is to do with CXHY, and then we can balance our equation with X plus Y over 4 oxygen O2 to give us X CO2 gas as well as Y over 2 H2O. Complete combustion of hydrocarbons. And this thing here, 2 moles of alkane, you get 665 dm cube of carbon dioxide. So if you get 2 mole of these, We need to be careful here though. This is 665 dm cube, and this is at 400 Kelvin and 1 times 10 to the 5 Pascal. The more I think about this, the more this seems like an ideal gas question, because this is not room temperature and pressure. If it is not room temperature and pressure, we can't really do much calculations with the 24.0 dm cube per mole of gas, which is only valid at room temperature and pressure. If we think about PV equal to nRT, the ideal gas equation, what do they want? They want the formula of the alkane. So perhaps in this equation, we can be thinking about, what can we be thinking about actually? I don't know what can we be thinking about. Let me think. Let's see, PV equal to mass over mRT. What can I do? If I have the mole of the alkane, if I have the temperature, and I have the pressure and the volume, there's not much use at all. PV equal to nRT is not going to be much use because we already know the mole of the alkane. What is the formula of the alkane? This is not very good at all. Let me think. Okay, I think I see it. So this one is carbon dioxide. So this is the volume of carbon dioxide. So perhaps we need to find the mole of the carbon dioxide first. If we get the mole of carbon dioxide, then we can relate that the ratio here to the mole there, and we should be able to work out what is X and move on from there. So if we imagine that one is carbon dioxide, assuming carbon dioxide behaving as ideal gas, so the mole of the carbon dioxide is going to be PV over RT. So our pressure is 1 times 10 to the 5. Our volume there, this is in dm cube. So what is important is 1 dm cube is 1000 cm cube. So that means 1 dm. If you cube root both sides, you're gonna get 1 dm as 10 cm. But in ideal gas equations, our volume has to be in meter cube. So 1 dm equal to 10 over 100 meter. That is actually 10 to the minus 1 meter. So this is equal to 10 to the power minus 1 meter. Now all you have to do is cube root both sides, and I get my conversion factor, which is 10 to the minus 3 meter cube. So from that 665 dm cube, I just have to multiply by minus 3, and then I will get the conversion for dm cube to meter cube as required in the ideal gas equation. So R is given in the data booklet, which is at the back of this sample paper. Since there is no more separate data booklet, R will be given at the end of this paper in the question paper itself. The temperature here is 400 Kelvin. It's already in Kelvin, so we are nice and easy going like that. So there's the mole of CO2. Press that into calculator, and I get 20.0 mole. So what we get really is we have 2 mole of CXHY, and we get 20.0 mole of CO2. Having done that, you can see 1 mole is to X mole. So if we convert this into 1 mole, that means we have to divide by 2 in order to compare our coefficient there, which is 1 mole give us X mole. So 2 become 1 is divide by 2. So 20.0 divided by 2, which is 10.0. So X is equal to 10.0. If X equal to 10, there can only be one answer, which is option C there. Question 9. So which one will give you the standard enthalpy change of combustion of methane? If I write an equation, the combustion of methane, CH4 burns completely in oxygen, in excess oxygen, CO2 and H2O. So balancing our equation, we get 2 H2O like that, and we need to have 2 O2. These are all data information. They are all data information. Of course, we can write carbon as an element. So this is gas, and liquid at room temperature and pressure. Under standard conditions. So these are the stat symbol. And then hydrogen, 2 of that hydrogen gas as an element. And then O2 there, 2 of that. So here, going upward, this is the formation of CO2. This is 2 times the formation of H2O, because we are forming 2 mole of H2O from its element there. And going upward here, this is the formation or CH4, and the formation of this element oxygen from its element is obviously 0, zero, because enthalpy change for the formation of element from itself under standard conditions can't mean anything at all. So this is the combustion of CH4 going that way. So we can think of it as like this Hess law going this way. Hess law says the enthalpy change of a reaction does not depend on which path you take, whether it's direct or this indirect path. As long as you start from the same reactant and end the same product, the enthalpy change will be the same. So since this is going opposite way, so this will be minus the formation of CH4. So here is a plus the formation of CH4. That one is wrong already, so A is wrong. Plus the formation of CH4, that is wrong. We're looking at minus the formation of CH4. We're looking at minus the formation of CH4, so only D can be the answer. Minus the formation of CH4 plus the formation of CO2 plus 2 times the formation of water, only D can be the answer there. Question number 10. This is about oxidation number. Oxidation number, you look at one species only without looking at the number in front of the equation. So for ClO minus 1 overall oxidation number, you have 1 oxygen. Each oxygen is minus 2 in that species. The overall oxidation number of the ion is the charge of the ions. So chlorine there is minus 1 plus 2. Chlorine is plus 1 there. ClO3 minus, case study, this is called chlorate 5. I'm just going to show you how it is chlorate 5. So 3 times minus 2 there, minus 1 plus 6, that one is plus 5 there. And of course, oxidation number of the ion itself is just the charge of the ion itself. So looking at all that, we're looking at plus 1, plus 5, and minus 1. So there's option C there. Question 11, this is about using changes in oxidation number to help balance redox equations. Again, it's to do with oxidation number. So we look at MnO4 2 minus 2 overall equal to 1 manganese. We have 4 oxygen, each of which is minus 2. Manganese is minus 2 plus 8. Manganese is plus 6 there. Then you have this MnO4 minus, your classic oxidizing agent when it is acidified. So there is manganese 7. Let's just show that it is manganese 7. There are 4 times oxygen. Each oxygen is minus 2. The manganese is minus 1 plus 8. The manganese there is plus 7. Manganese 7. MnO2, manganese 4 oxide. So 0 for this overall compound. Compound has no charge, so 0 overall. 1 manganese, 2 oxygen. Each oxygen is minus 2. So you got 2 oxygens, so there's plus 4 there. Using changes in oxidation number, so this is manganese plus 6, this is manganese plus 7, and this is manganese plus 4. So let's have a look. Plus 6 going to plus 7, this is an increase of 1. And then on the other side, we have minus 6 going to plus 4, this is a decrease of 2. So changes in oxidation number must be balanced. So since this is minus 2, this is plus 1, the lowest common multiple, primary school mathematics, 2 and 1 is going to be 2. So this one just have to multiply by 1, keep out with itself, so D must be equal to 1. If I just use a different color, let's just use the black color one, so times 1, so therefore D must be equal to 1 since you can only have 1 of that. And this one must be multiplied by 2, and that means C must be equal to 2. C must be equal to 2 because use changes in oxidation number to help balance redox equation. If C equal to 2, there can only be one answer, which is option C there. And why in the world is this 3? Because here you get 2 manganese, and here you get 1 manganese. So 2 plus 1 manganese will give you 3 manganese. A equal to 2 manganese there for C, and then 1 manganese for D. So 2 plus 1 equal to 3 there. So that's why C is the correct answer there. Question 12, this is about Kp. So Kp expression, the power to which you raise the partial pressure is to do with the number in front. So this is 2pH2 squared, that one is definitely wrong already. This is 2pH2 squared, that one is already wrong. We know that it's to do with the partial pressure of the product, the stuff on the side, on the right hand side. So it's a CH3OH to the power of 1. And then divided by the partial pressure H2 to the power of this mole ratio in the balance equation. These are the reactants, so the partial pressure appear at the bottom. So C is the only correct answer there. Question 13, we have 4 grams of powdered calcium carbonate, also known as limestone. So sometimes questions say limestone, so that's basically just calcium carbonate, among other things, I guess. And then you add it to hydrochloric acid, so very clearly you get a salt, carbon dioxide as well as water. And this is a rate of reaction. The carbon dioxide produced is recorded every 30 seconds, and you will see that the reaction keep on producing gas until 210 seconds. Then no more gas get produced, so no more gas forms because the reaction has completed, so no more reaction. That means the rate will decrease. No more reaction there. Why does the rate of reaction changes with time? Well, if you look at this one is plus 30, and then 88 minus 70 is plus 18, and then 101 minus 88 is plus 13. Sorry, that was plus 18, this is plus 13. 110, that one is plus 9, this one is plus 6, this one is plus 4. What you notice is that there is less and lesser gas. There are lesser gas produced at every 30-second intervals. So you can see that the rate of reaction slows down. So the rate decreases. And why does the rate changes? Well, we know that it decreases. Decreases mean there must be fewer collisions because the reactant get used up. So there's lesser reactants. Lesser reactant mean lesser colliding particles, and therefore you get less successful collisions, and therefore your rate of reaction naturally will decrease as the reactant get used up. Definitely not more collision, because this rate of reaction definitely gets slower. Over the same period of time, there is lesser gas getting produced there. So that's to do with this thing here. Which one is limiting? Which one is limiting the reaction? And this is really a question about mole concept. So we get 4 grams of powdered calcium carbonate. So the mole of the calcium carbonate is equal to the mass over the mR, since we are given reacting masses. And this divided by 100, since we are already given in the questions, we get 0.04 mole. And then we have the mole of the HCl. These are solution chemistry. These are aqueous hydrochloric acid, a substance that dissolves in water to give you H plus Cv. Concentration in mole per dm cube. The volume has to be converted to dm cube in order for the formula units to cancel out, in order for the math to make sense. So what we get is 0.01 mole. Hope you can see that in the balance equation, you get a calcium carbonate plus HCl. You're going to get Ca2 plus Cl minus. So, CaCl2. And you're going to get H2O and CO2. Balancing the equation, 2 chlorine on the right hand side. So you need 2 HCl, and the 2 hydrogen plus 1 oxygen give you H2O. This one lose 1 oxygen and you get CO2. What we can see is 1 mole of calcium carbonate reacts with 2 mole of HCl. So 0.01 mole of HCl would only react with 0.005 mole of limestone, of calcium carbonate. So this one is in excess. This one is limiting. So this one is the one that will get completely used up. So the correct thing to do here really is to choose the hydrochloric acid, as that is being used up. Therefore, you will get the reaction slowing down. That's why you get lesser gas produced over time. Question 14, this is about correct statement for the ideal gases. And we talk about zero particle volume as stated in the syllabus under this ideal gas. If you look in the new syllabus, the 2022 syllabus onwards, as this is what the sample paper is for, this is stated in the syllabus, and we talk about negligible intermolecular forces, which they say you can assume to be no intermolecular forces. Okay, because this is assumption of ideal gases, the assumption is that no intermolecular forces. Of course, in the real gas, you can have weak intermolecular forces, but the weaker the intermolecular forces, the more ideal it gets. Okay. Question 15, we have a couple of these things here. We want the mole fraction of hydrogen. So this is to do with mole fraction. Mole fraction, what is mole fraction? So mole fraction is to do with the mole of the substance, the mole of that substance, divided by the total mole. And these are all gases, right? So our gases here, hydrogen exists as H2, nitrogen exists as N2, helium exists as single atom, If you look in the data booklet, which you will be given the question paper, you will have periodic table. This is 2 times 1.0, 2.0. This one is 14.0 times 2. You will get 28.0. And then this is just relative atomic mass because it doesn't exist as a molecule. This one will just be 4.0. So what do we know? We have the total mole. We have the total mole at equilibrium. Well, what do we want actually? We want the mole fraction of hydrogen. So what is the mole of the hydrogen? The mole of the hydrogen is 12.0 gram divided by 2.0. This is the mole of the hydrogen. At the bottom, I need to total up the mole at equilibrium. The mole of hydrogen, mass over mR. The mass, the 42.0 divided by 28.0. So 42.0 divided by 28.0. That is the mole of N2. Last but not least, I have 4.0 gram of helium. So add them up all together. This again is in terms of mole. The mole and the mole cancel. So don't know, what do we get on the calculator? So 12 divided by 2 plus 42 divided by 28 plus 4 divided by 4. So I get, at the bottom, make sure you actually do them in brackets. I get 0.706. And that has to come close to 0.71 as the correct answer when you round it up to 2 decimal place there. Now question 16, what is the definition of bond energy? So we talk about bond energy. So in the data booklet, in the old days, you will talk about data booklet, and the definition is in terms of everything in the gaseous state. You break 1 mole of the covalent bond, 1 mole of the covalent bond to form gaseous atoms. Everything in the gaseous state, this is the definition of BR bond energy. So is the energy required? All are correct. To produce is, hang on, let me see what they're producing. We are not talking about producing the atoms because that will be in A2. This is to do with atomization. Atomization is now in A2 topic, so it's in terms of forming the atoms, but bond energy is to do with breaking 1 mole of the covalent bond, and this must be in the gaseous state, as that's how bond energy calculation works. Everything must be in the gaseous state. Fixed definition stated in the syllabus. Question 17, we're talking about the melting point against relative electronegativity. So electronegativity is slightly easier to understand in the sense that fluorine is the most electronegative element, and going right to left, then this one become less electronegative, and going down the group, this one become less electronegative. So if we go on to the next period from left to right, we will have magnesium, and then we will have aluminium, and we have silicon and phosphorus. On the x-axis, this electronegativity will increase going from left to right. So we should have magnesium, aluminium, silicon, phosphorus, electronegativity. This is fine on the x-axis. Magnesium, aluminium, silicon, phosphorus, it is fine because this is the value, this is the value, this is the value, this is the value. The x-axis again is fine. This is not fine. This is saying that magnesium is more electronegative than phosphorus. That is not right because electronegativity increases across a period, because we know about this trend about fluorine. So on the x-axis, this is already wrong. On the x-axis, these are already wrong there. Now looking at A and B, without even really checking the melting point, without even knowing the melting point, you know that A is wrong because in terms of melting point, silicon will have the highest melting point because that thing there has a giant covalent structure. So just like diamonds and graphite, giant covalent structure, you need to break many strong covalent bonds, and that is why it will have the highest melting point out of all the period 3 elements. In terms of the actual trend, of course, you are expected to be able to sketch the metallic bond gets stronger, and then suddenly it goes all the way up to silicon, and then it drops all the way down to P4, and then rises out a little bit to S8, go all the way down to Cl2, and then go further down all the way to argon there. So if I just label this sodium, magnesium, aluminium, the silicon will have giant covalent structure all the way up there. The metallic bond gets stronger. You get a slight drop all the way because these are simple covalent molecules, but it increases slightly because the van der Waals are stronger as a result of the actual number of atoms in one single molecule there. So Cl2, and then argon is just single atom there. But just by looking at silicon, you can tell that, you know, aluminium doesn't have the highest melting point because this is just giant covalent structure compared to giant covalent structure compared to giant metallic structure there. Okay, so this one is definitely wrong. So, you know, correct answer there must be B. Question 18, we have an excess of MgO shaken in water. We know that MgO is not very soluble in water. That is why your MgOH twice not very soluble. Solubility of group 2 hydroxide increases than group 2. This is not very soluble, it's only pH 9. This barium hydroxide on the other hand is very soluble. So you get a very strongly basic solution pH 14. So from the first one, the filtrate will have a little bit of what are we doing actually? It's what am I doing? Let me do the second one first. The filtrate X there is definitely barium hydroxide, as that is completely soluble. That is called filtrate, substance that pass through the filter paper. You add some sulfuric acid to this. So when you have barium hydroxide plus sulfuric acid, you expect to get neutralization, which you do. But then you also get a salt, which you do. But this thing is insoluble. Insoluble white precipitate. You know this from your test for sulfate, obviously. So observation or addition of sulfuric acid to the filtrate of higher pH. The higher the pH, that is going to be the more alkaline solutions. So more basic, more alkaline. So the one which is more soluble hydroxide will be the more basic. Since this is more soluble, this filtrate will be belonging to X. That is the more alkaline one. That is barium hydroxide. And when you add sulfuric acid to this stuff of barium hydroxide, you're gonna get a white precipitate. That is your test for sulfate there. Question 19. So we are doing some thermal decomposition until no further loss in mass because all the carbon dioxide would have been driven off. So blah blah blah, what is happening? So if we have MgCO3, that's going to decompose to MgO and CO2. This is R. This is crucible R is heated until no further change. And then we don't heat crucible S. So in S, we still have magnesium carbonate. That is very, very important. So now, when we add hydrochloric acid to both crucible, so if we have R, and then if we have S, what is going to happen is the MgO, which is a basic oxide. So basic oxide can react with acid, and you will get a salt, and you will get water, balancing equation obviously. So there is no gas produced with R because this is just a neutralization between the acid and the basic oxide. So no gas produced with R because you only have MgO that reacts there. Whereas here you have MgCO3 because the carbonate hasn't decomposed at all since you didn't heat it. It will react with acid. So just like earlier questions, carbonate reacts with acid to give you the salt. In this case, you get magnesium chloride, Mg2 plus Cl minus, you get CO2 gas and you get H2O. Of course, balancing equations, you definitely see an effervescence from the CO2, which you test with lime water and it will turn lime water milky. So gas getting produced there is correct. Question 20. So this is a reaction of concentrated sulfuric acid with sodium iodide. If we think about our oxidizing power of the halogens, as you will see a lot of these in my topical playlist, which of course remain free for everyone to use. So Cl2, Br2, I2. Where is our consulfuric acid? It lies somewhere in between the oxidizing ability of bromine and chlorine. So with these iodide, which is a much stronger reducing agent, so I-1 is a much stronger reducing agent, what's going to happen is you're going to get sulfur 0, you're going to get I2, which is iodine 0, and then hydrogen sulfide H2S, the sulfur is -2 there, and sulfur dioxide, where the sulfur is +4 oxidation number. So hydrogen sulfide is the product of a reduction reaction. That is entirely correct. This is the lowest oxidation number that sulfur gets to, which is -2, and this get reduced all the way from sulfur +6 in sulfuric acid all the way to sulfur -2 in hydrogen sulfide. Looking for which one is correct. So A is correct, but let me just go through the other options and prove that they are not correct. So iodide ions are not stronger oxidizing agents, they are stronger reducing agents, obviously. And part C, option C, sulfur atoms are both oxidized and reduced. Not really, they don't get oxidized further. Sulfur +6 in H2SO4 is already the highest, it doesn't go any higher. They do get reduced though, so you know, the oxidized bit is definitely wrong. Sulfur atoms from sulfur acid are oxidized. Nope. This is sulfur +6 in H2SO4. H2SO4 is a molecule, it's a compound, it's got no charge, 0 oxidation number. It's got 2 hydrogen, which is +1 hydrogen in a compound. And then the sulfur is what you want to find. You have 4 oxygens. Each oxygen has an oxidation state of -2 in this H2SO4. So the sulfur there is +8 -2. The sulfur there is +6. And you get sulfur +4 in SO2 there. So you know, overall this is a reduction and not oxidation. In this question 21, so this is about certain conditions. This is the hot concentrated condition, I guess, for sodium hydroxide. And what is happening? Yep, this is the more concentrated NaOH, the hot concentrated NaOH. This is the more extreme disproportionation reaction. So in terms of what we get, if you think about it, there's Cl2 plus NaOH. That is going to give you chlorine -1. Instead of stopping at chlorine +1, it's going to go all the way to Cl +5. This is ClO3 minus. It's going to give you NaClO3. I'm just writing them as ionic form so that it's easy to follow. And of course, you also get water. But when we balance our equations, so we know C is definitely our answer. Use changes in oxidation number to help balance chemical equation. This is a -1, whereas the other one is a +5. Of course, use changes in oxidation number to help balance chemical equation. Times 5 there, times 1 there. So that means we must have 1 of these. We must have 5 of these, and 5 plus 1 sodium. We must have 6 sodium hydroxide, and we must have 3 Cl2 because 5 and 1, 6 chlorine, so 3 Cl2 there. Usually I don't circle these things, so I probably shouldn't circle them at all because you know these are balancing the chemical equations using changes in oxidation number. Of course, the water also needs to be balanced. 6 hydrogens, so 3 H2 all there. But this question is not asking you to balance the equation. It's asking you for the formula of this other product, the other chlorine containing product, in addition to the chlorine -1 in sodium chloride there. Which is why you get 5 mole of this sodium chloride and 1 mole of this NaClO3. Question 22. Redox reactions are common. So this is related entirely to what I talked about earlier. It was this chart. Well, not chart really. Oxidizing ability of these halogens. So we talk about this oxidizing ability of the halogens, which means when you go backward, you're talking about the reducing power of the halide. I talk about a lot of this in my topical tutorials as part of the AS level chemistry. So do check out those topical playlists. And what do we know? We know that Br- ions reducing Cl2 but not I2. So Br- is a stronger reducing agent than this. So it will reduce Cl2. Or you can think about the other way around. Cl2 is a stronger oxidizing agent than Br2. So this one can oxidize Br- to the other ones. But Br2 is stronger than I2. So that one, what's happening? Br- will reduce Cl2. Oh yeah, Br- can reduce Cl2 to Cl-, but then Br- cannot reduce I2 to I- because this is stronger. It's going that way there. So in terms of correct statement, A must be correct. What is wrong with B? So Cl2 is stronger oxidizing agent than Br2 than I2. So this thing is wrong. It says but not I minus. It's actually wrong. It will oxidize Br minus to Br2. It will also oxidize I minus to I2 then. F2 is above chlorine. You would expect where the F2 is B. The F2 will be slightly higher oxidizing ability than Cl2 because it's above chlorine in the periodic table. So it's not the weakest, it is the strongest. And what is wrong with D? I minus is actually the strongest reducing agent out of this list, including the fluoride. So, it becoming better reducing agent. And state an example of a good reducing agent, Ki. K plus, I minus, very good reducing agent. D is definitely wrong. It's not the weakest, it's the strongest out of this particular list of halide ion that you have there. So A is the only correct statement there. Question 23. So which statements describe a trend in period 3 between every pair? This is playing around with words really. Adjacent elements from sodium to chlorine. So we really need to be able to draw some stuff. We know the atomic radius decreases. So this is to do with atomic radius. They are not asking on ionic radii, but we also know that ionic radii would decrease like this up to Al3 plus and a plus like that. And then this pink one will be the P3 minus all the way to Cl minus. These are the ionic radii. They say describe a trend between every pair of adjacent elements. Atomic radius decreases, so that one is very clearly true. I think A is definitely the answer. As for the ionization energy, that can't be because we know that specifically there is an increase, there is a decrease between group 2 and 13. There's an increase, and then there's a slight drop between group 15 and group 16. As you fill up the P3 to P4, the paired electrons repel more than the unpaired electrons. That was one of the earlier question. This is group 2 going to group 13. You're filling in a new P subshell further away from the nucleus, therefore more shielded and slightly easier to remove that. So it's not all decreases, there is some specific drop there. And melting point decreases, that is not entirely true. I'm just going to go back to the previous question. The melting point of the third period element. The melting point of the third period element was covered back then. So I already discussed it when we discussed question 17 earlier. This is the correct trend for the melting point of the period 3 elements in terms of the structure and bonding. So a lot of these are related together, yeah. So obviously this one is for this question as well. So melting point decreases is not true. It goes up and down. Electrical conductivity, it doesn't increases. We know that it goes from metal to non-metal. So a metallic bond gets stronger. Silicon is a semiconductor, but then it drops all the way to 0 when it's phosphorus, sulfur, chlorine, argon. So these are all non-metals. There are no free electrons at all. Whatever we do with graph, we have to label the axis so that they know what we're talking about. It's not all increases. It does increase, but not for every pair of elements all the way from sodium to chlorine. So be careful to read the questions. Only A can be the answer there. Question 24. Nitrogen forms polyethylene oxide. Why? When you oxidize Y further, so we are thinking about nitrogen and sulfur chemistry, but it could be something else as well. Which statement is correct? So you get 1 mole of Y reacts further with half mole of gaseous oxygen, and that will go to a high oxidation state. If we look at N2 plus O2 give us 2NO. NO plus half O2 give us NO2. And this happens in the atmosphere. Of course, it could also be sulfur, I guess. No, it cannot be sulfur because this question is about nitrogen. That's what is stated there. So compound Z, so we're looking at compound Y must be NO. So NO there must be Y. And then compound Z must be NO2. So compound Z does not react further in the atmosphere. Does not react further in the atmosphere is incorrect. We know that NO2 plus SO2 helps to catalyze the formation of SO3, and that will go on to form acid rain in the upper atmosphere. And then it's a catalyst, so it gets regenerated to give you the NO2. And of course, the SO3 now can react with the rainwater, and that will give you the acid rain without going through oleum or anything, because this happened in the atmosphere. This is not in industry. We don't have to worry about exothermic fumes, etc., etc. Next one, a molecule of Y. So Y is NO. We need to count the number of electrons. Before you count the electrons, count the protons. So the number of protons in NO is going to be 7 protons for the nitrogen. The atomic number of nitrogen is 7, plus 8, which is the atomic number for oxygen. So you have 15 protons. And this is a molecule. Molecule is uncharged. And why is molecule uncharged? Because the number of electrons must be equal to number of protons. So 15 electrons is true if you have 15 protons. Okay. The next one is definitely wrong. It increases by 1 because, you go from NO to NO2. This is nitrogen plus 2. This is nitrogen plus 4. This is an increase of 2 oxidation number there. And as for why D is wrong, Y is non-polar. That can be nitrogen, oxygen, different electronegativity. Very clearly, 2 atoms, different electronegativity. Definitely it should be polar molecule and not non-polar. Okay. Question 25, we are moving on to organic chemistry now. So structural isomerism and stereoisomerism. We need to consider those things. So each of these carbonyl compound reacted with NaBH4. So this is a reducing agent. And when we reduce that, we are going to get butane 1-ol, which is a primary alcohol. Butanone is going to give us butane 2-ol, which is a secondary alcohol. Pentane 3-ol will give us pentane 3-ol, and this one is like that. So the carbon with the OH, is bonded to 2 other carbons. This must be a secondary alcohol. Propanone will give us a secondary alcohol, which will be this one here, which is propan 2-ol. So secondary alcohol, the carbon with the OH is bonded to 2 other carbon there. The product of each reaction is heated with Al2O3. So this thing here is elimination. So you are trying to do elimination of alcohol, and elimination of alcohol will produce alkene, and it will kick out the H2O, which will come out as steam. Because you're at 600 degrees Celsius, you don't produce water, you will produce steam. Okay, so be very careful there. Anyway, you want to produce the MOS isomer. So we're going to have to try and sketch out some stuff. So if I sketch out, first of all, butane 1-ol, 1, 2, 3, and 4. There is only 1 hydrogen to be eliminated there. So, you're going to get a double bond there as you remove that. So what are you going to get? You're going to get only 1 isomer. So most likely A cannot be the answer. There is no cis and trans as well, because these are CH2 terminal group. They are the same atoms or same group of atoms on one side of carbon-carbon double bond, no cis and trans. We have this alcohol now. Well, we can see this. This is a hydrogen of a CH3. So this is different. And this one will give that. But we also have a hydrogen there. This is a CH2. This was a CH3, so this green and the blue one are clearly different. So when I go for the green color one, I will get this. But that is the trans isomer. And I can get the cis isomer like that. So there are 3 already. I don't think I'm expecting any chiral center, even though they have mentioned about stereoisomerism, because all I'm getting is just alkene with no other functionality. If I have this secondary alcohol, if this is option C here, this hydrogen is the same as this hydrogen, because this is a symmetrical molecule exactly in the middle. So you could say you could get this, which is the same as this. They are the same. So do not count them twice, but instead you could get the cis and the trans like that. So that one will be the trans, and this one will be the cis. Okay, As for the last one, what do we have? Actually, what do we have for the last one? We have propane 2-ol. So again, it's a symmetrical molecule. So this hydrogen is the same as the hydrogen. CH3 there. I'm just gonna show you one, and there's no other isomers, just one there. So altogether, this one gives you the 3 isomers, which include the geometric isomer cis and trans there. So B must be the correct answer there. Question 26, we have cortisone. So in addition to those chiral centers marked by asterisk, in addition to, they also highlighted other. So you cannot count this already being asterisk. How many other chiral centers are there? Look for ring junctions. So I'm highlighting this green one. There's one. These are double bonded, so automatically they cannot have a chiral center. These are CH2, carbon form 4 bond, 1, 2. So there are 2 other hydrogen. Carbon form 4 bond, there are 2 other hydrogen there. So this will already mark the ring junctions. There's another ring junction here. This is a CH2, cannot be chiral. There's another, this is not ring junction, this is OH, and then this bit with the ketones, and then this side hasn't got the big part of the ring, this side's got a big part of the ring, so this is different 4 groups on the carbon there. This one is already marked, this one is CH2, this one is double bond. So altogether, I think, let me just double check. No, already, nope. I just marked this one, 1, 2, 3. So there are 3 additional green mark here. There are the additional chiral center in addition to this already marked in asterisk. Yeah. Question 27, you react an alkene. Alkene reacts with acidified manganese 7. So this is oxidation of alkene. And the organic product has a relative molecular mass greater than. So this is not cleavage or rupture of carbon-carbon double bond. So this is not extreme oxidation. If it is not extreme, therefore it must be mild oxidation. If it is mild oxidation, we are going to form diols. So add OH onto both carbons. If you add OH onto both carbons, you plus 17 and plus 17, because plus 16 and 1 plus 17 onto both carbons. Altogether, you get plus 34, and that must be cold and dilute acidified CmNO4. This is the mild oxidation of alkene carbon-carbon double bond. If you rupture, you will end up with lesser mass compared to the starting alkene, because you will rupture this totally depending on the 3 different type of functionality you have on alkene as stated in the oxidation of alkene syllabus. Question 28. So this polymer, this is part of the short chain of addition polymer, and this is an polyethylene, I guess. This looks like it's a repeat unit there and there. So we have a relative molecular mass of around 10,000. So each repeat unit, so you can see each repeat unit is CH2 like that. So that thing there, the MR is going to be, the MR of the repeat unit is going to be C2H4 like that. So 12.0 times 2. And you get 4 times 1.0, you get around 28.0, I guess. Now, what happened is the whole polymer, 10,000 MR divided by 28.0. So give or take, how many monomer is that? So that is around 357 monomer units. Okay, there's around 360 if you round it up approximately. So these are not super exact numbers to begin with. Question 29, so you have a lactite. This is an intermediate. Now you are heating with an acid catalyst. You want to produce lactite. So lactite is an ester. You can hopefully see that this is an ester. So they're asking you, which one, when you heat it with acid catalyst, can produce this? Well, if you try to form the ester, then now try to break up the ester. This is the bond that you need to break in the ester. Let me just show it in pink. So that is the new bond that you form when you form the ester. So what we're going to do is we're going to do hydrolysis of ester. We're going to get that. So this OH is actually something new. So this is OH. and then you get a new, oops, sorry, you get the all O, but then you get the new, the new hydrogen like that, and then you get the all bit here, O, and then that one, and then the all O, and then you also get the new OH like that, and then you get the new OH there. Okay, so this and this thing on the left and on the right, they are the exact same thing. So we just need to name this molecule. So this molecule here, if we name the longest chain carbon 1, 2, and 3. Of course, you could do the other way around 1, 2, and 3, but carboxylic acid has the higher priority, so this has to be carbon 1. So this is 2-hydroxy, and then propanoic acid because 3-carbon acid, so propanoic acid, and then you have 2-hydroxy because you have a OH at position 2, so option C must be correct there. So when you put these two reactions together, when you put two of them together, and then they will come together to give you that is actually going to be a reaction to form ester. So the reaction to form ester, as stated in the introductory organic chemistry, is called a condensation reaction. The syllabus never ever mentioned esterification. If you look in the syllabus under introductory organic chemistry, they never ever mentioned condensation. Instead, they mentioned condensation reaction. They don't say esterification, they say condensation, not esterification. When you form this ester, you kick out H2O. When you form the other ester, you kick out the other H2O there. Question 30. So you get diols, as we mentioned in one of the earlier questions, the maloxidation of alkene there. So this hydroxy group, so when you have two hydroxy groups bonded to the same carbon, they can eliminate. Eliminate means you kick out what? Kick out water to produce a carbonyl compound which has C double bond O. Now, which one is hydrolyzed to form a compound that give a positive reaction with 2,4-D and pH? So this one will give orange PPT, and that will tell you that it is ketones, or it could be aldehyde. So it could be ketones or aldehyde, but not with phalanx. So not positive with phalanx. So phalanx is blue solution. So phalanx remain blue. So there's no reaction at all. So this is not aldehyde. Therefore, it must be ketone. So we're looking at something which is ketone, all right? But we have to follow this thing here where we have to eliminate the water molecule. So if we look at A, we have propane, so 3 carbons. We have 1,1-dibromopropane. So when we replace it with OH and OH, because this thing here will form diol. As you form the diol, then you will eliminate, from this thing here, and you will get an aldehyde, for instance, like that. Something like that, okay? So you get this aldehyde here, and that is not a good story because that is not what you want. You want a ketone, you don't want an aldehyde, so A cannot be the answer. How about B? You have 1,2-dibromo, so 1 and 2. So if I get OH and OH, well, they are not on the same carbon, so they cannot spontaneously eliminate a molecule of water because they are not on the same carbon. So 1, 2 is bad because not on the same carbon, which means 1, 3 is also bad because they are not on the same carbon. So I'm pretty sure D is the correct answer. Let me just double check with D. So what happened with option D? We have 2,2-dibromo like that. When they get hydrolyzed, you're going to get OH and OH. And then, of course, because they are now on the same carbon, we can eliminate H2O. And then we will get a ketone. So this is propanone. And this is as required in the questions where we will get orange PPT, a positive reaction with 2,4-D and pH, but it will not be oxidized by phalanx. And the phalanx solution will remain blue there. So D must be the correct answer. Question 31, X and Y are the reagents. So you're converting 1-bromopropane. So this is 1-bromopropane. And it's converted to butanenitrile. So make sure you can spell this properly and name it properly because you have added 1 extra carbon, important carbon, added 1 carbon, now 4 carbon. And then this is a nitrile as stated in the AS syllabus. From the nitrile to the carboxylic acid, this is the hydrolysis of nitriles. So you are trying to hydrolyze nitriles there, and you get a carboxylic acid. If you do a base hydrolysis of nitriles, you will get the salt. Therefore, it cannot be basic hydrolysis, it must be acidic hydrolysis. That's why it remains carboxylic acid. So that thing there will be base hydrolysis. So look at the product, that doesn't make sense at all. So it cannot be the base hydrolysis there. So B and D are out. Between A and C, so this and these are okay. This one is a nucleophilic substitution. So the type of reaction has to be substitution. As stated in introductory organic chemistry, the mechanism here has to be the SN2, as this is a primary halogenoalkane and you're doing a nucleophilic substitution. So it is best if you have a good nucleophilic source, delta minus, delta plus, one single step SN2 mechanism. CN minus source doesn't come from HCN. HCN is simple molecular. It doesn't dissociate very much at all. You will see more in A2, I guess. So it doesn't dissociate very much into the CN minus at all. So we need a good source of a nucleophilic source, which is a full ion. So KCN in ethanol for these nucleophilic substitutions of halogenoalkane there. Question 32. So this is a compound with these molecular formulas, C4H10O. You can oxidize with acidified potassium dichromate, can be oxidized. So you will see the orange color. So this is chromium plus 6, which is orange in color. And this orange color will go to chromium plus 3. And this chromium plus 3 is actually chromium 3 plus aqueous there, orange to green, yeah? And this is green in color. So Q cannot be made by reducing carboxylic acid with LiLH4. Cannot be made. What is Q? Well, let's go through one by one, I guess. If I draw out the skeletal formula, this is butane 2O because CH3, CHOH, and then CH2, CH3 can be oxidized. Yes, perhaps you can get all the way to ketone as this is a secondary alcohol. The carbon with the OH is bonded to two other carbons. But then Q cannot be made by reducing carboxylic acid. Well, carboxylic acid with LiLH4 will give the primary alcohol, so you cannot get this. So A must be the correct answer there. Okay, because carboxylic acid with that reducing agent, lithium aluminum hydride, will give you primary alcohol and it can never give you secondary alcohol. So that's why that's the correct answer there. You can try for the rest of these. This is a primary alcohol. The carbon with the OH is bonded to one of the carbons. Primary alcohol can be oxidized, obviously. You can lose the hydrogen on that carbon with the OH, and you can reduce carboxylic acid to give you back primary alcohol. This is a tertiary alcohol. Tertiary alcohol then cannot be oxidized because no hydrogen on the carbon with OH. If you don't have hydrogen there, you cannot lose what you never have to begin with, so you cannot oxidize it, so it doesn't even satisfy the first condition there. How about option D there? Again, it's primary alcohol, even though this one looks complicated, but the carbon with the OH is bonded to one of the carbons, so it's the same case with option B. You can get it by reducing carboxylic acid with lithium aluminum hydride to give you back your primary alcohol there. Question 33. So we have 2.30 gram of ethanol, which is C2H5OH. If I look up the MR, because we need to do some mass calculations, so 12.0 times 2 plus 5 times 1.0 plus 16.0 times 1 plus 1.0 times 1. I get 45, am I correct? That doesn't look so good. It should get 46. I mean, I've done enough chemistry my entire life that I roughly know when something doesn't seem so well, with experience and stuff. Now you boil it under reflux. So this is ethanol. So we expect the ethanol to go all the way to carboxylic acid, which is going to be C2H1234 and then O2. So the MR of that carboxylic acid is going to be 12.0 times 2 plus 4 times 1.0 plus 16.0 times 2. I get 60.0 essentially. Okay, so the most key thing is you boil it under reflux. If you already reflux it, then you separate out by distillation, you are not going to get aldehyde because you already reflux. You see, already reflux. If you already reflux, you didn't collect by distillation, cannot be aldehyde, must be carboxylic acid. Okay, now the yield of product is 60%. This is important. In your balance equation, 2 carbon give you 2 carbons. So what we can say is the mole of the carboxylic acid is to the mole of the alcohol should be 1:1. But then 60% means 1 mole of the alcohol will only give you 60% of 1 mole. So 1 time 60 over 100, which is, well, 0.6. On the other side, I want the mass of product. So this is going to be the mass of the acid, the mass of the carboxylic acid divided by 60, because mass of mR is the actual mole of carboxylic acid that comes from the actual mole of the ethanol, which is 2.30 divided by 46. This is my usual mole ratio, favorite method. So I just move up the bottom bit. So 0.6 over 1 times 2.0 over 46 equal to the mass of the acid divided by 60. I could of course save up some time, move up the 60 to the other side, and keep your working clean and tidy. So 60 times 0.6 divided by 1 times 2.3 divided by 46. I get the mass of the carboxylic acid product to be 1.8 gram mass over mR there. So option C is the correct answer. Question 24, we get a positive test with alkaline aqueous iodine. So we get a yellow PPT. This yellow PPT is called triiodomethane because the other name is called iodoform. 3 iodine, 1 hydrogen on 1 carbon. Compound R does not display stereoisomerism. Does not. So stereoisomerism means no cis and trans, but it also means and or optical, which is to do with chiral carbon. So we're looking at option A. So we have these ketones, and then we're looking at that. Well, we have a CH3CO. This will give you iodoform, which is positive. And then the second one is stereoisomerism. Well, we definitely do not have stereoisomerism because the question wants us does not display stereoisomerism. So does not display. That is true because it does not display. Okay, so be very careful about the question. But the fact that is, it's an iodoform. So iodoform is already positive. You will see a yellow precipitate, but it does not display stereoisomerism. Yes, it does not have stereoisomerism. So this one means no stereoisomer. There is no carbon-carbon double bond, and there is no chiral carbon, a carbon bonded to 4 different groups there. So A must be our answer there. This second thing was quite confusing there. But let me just go through option B. So what we have there is 1, 2, 3, 4. So I've got 4 carbon, am I correct? So I've got 1, 2, 3, 4. At carbon 2, I have a OH. And what do we have here? CH3CHOH. So this one is negative test. So because you don't have CH3CO or no CH3CHOH. So again, if this is negative, that can't be the answer already. You want positive, right? And the next one, I could see my CH3CO. But of course, I could see my chiral carbon there. If I draw C there, CH3CO, and then I have that. You can hopefully see there is a chiral carbon there. Oops, that carbon there. So it has a chiral carbon. So that second condition is already not fulfilled there. Even though this is a positive iodoform test, it should be positive there. And last but not least, you have a CH3. Actually, this is no iodoform because if you look at D, this is CH3, and then COH, like that. Am I correct? No, that's not correct. It should be this, and then aldehyde. So CH3 twice, and then carbon with no hydrogen. CH3 twice, carbon with no hydrogen, bonded to OH, CHO. So here, I do not have CH3CO. I do not have CH3CHOH. So again, no iodo form there. No iodo form, but you want positive iodo form. So definitely A was already just the only answer. I was just going through the rest to convince that they are definitely not the answer there. Question 35. What do we have here? We have citral. So we have aldehyde. We have alkene. So that and that is just normal alkene. And urea will access H2 and nickel. So this one will do reduction. The reduction of both the carbon-carbon as well as carbon-oxygen. So what you're going to get, so draw skeletal. So here originally was like that. So you're going to get an alcohol like this and like that. Now if you have hot concentrated acidified KMnO4, you're going to oxidize the primary alcohol. Carbon with the OH is bonded to one other carbon. You're going to oxidize it all the way to carboxylic acid. So you lose both the oxygen there, and then you just become carboxylic acid. So what could compound WB will not survive. It will be carboxylic acid. As you could see, everything has been hydrogenated or reduced, but then this last bit came from the primary alcohol. So these two carbon from the double bonds, the CHO become the alcohol, and this one gets all the way to carboxylic acid when it gets oxidized under reflux. So B is our only correct answer there. Question 36. We're talking about geometric isomers. So which statement is correct? Well, if they are geometric isomers, they give different products. Well, you're trying to contradict the statement, you see. You're trying to contradict the statement. If I have symmetrical alkene, this is a trans isomer because I could have the cis isomer. Now, they give different products. If they are geometric isomers, they will give the same products because, you know, even if I have this and that, because once you break the carbon-carbon double bond, you're not going to have the carbon-carbon double bond anymore. The left, well, I mean, they will give you the same product. So, you know, it cannot be different product. It will be the same products. Different empirical formula cannot be because they have the same molecular and also structural formula. But the key thing there is stereoisomer including geometric isomers. They just have different orientation or arrangement of the atoms, all the groups of atoms in space. Different empirical formula is impossible because they have the same molecular formula. Different functional group, nope, they are both alkenes. Different skeletal formula, yes, I have just drawn different skeletal formula. This is a cis where they're on the same side. These are the trans where they're on different sides. What is correct? Option D is correct there. Question 37. What do we have? We have 3 chloroalkanes. If I just draw the skeletal formula, let this be like that. And then what do I have here? That, and that. So CH3 twice CH, carbon from 4 bond, CH2Cl, that. Which statement is correct? Well, the carbon with the halogen is bonded to 2 other carbons. This is secondary halogenal alkane. I better write it properly. And then this is primary halogenal alkane. This is tertiary halogenal alkane. So the carbon with the chlorine, the carbon with the halogen is bonded to 2 other carbons. The carbon with the halogen is bonded to 1 other carbon. Hang on, not alcohol, but RX, halogenal alkane. Here is tertiary. The carbon with the halogen is bonded to 3 other carbons there. Now SN2 mechanism, it will favor the primary halogenal alkane. So we're looking at this, which is primary halogenal alkane. That is going to be correct. So it seems like we got our answer there. Okay. B is not entirely correct because rate of reaction there, the first step in this tertiary carboxylic ion is slow because it proceeds via SN1 reaction. So the first step of SN1 is very slow. It is what you call the rate determining step. Chlorine atoms in the 3 chloroalkanes are attacked by OH minus. That is wrong. It's actually the carbon delta plus, not the chlorine, which is delta plus. Molecular formula of the major product is C4H8. Molecular product of the major product. Molecular formula. Okay, I agree the molecular formula is going to be C4H8. When you eliminate this, you could eliminate from there, Or you could eliminate from this one, where you will get like this, and then the blue color one will give you like that, and of course like that. So all of these will be C4H8. The molecular formula of the major product. Just give me a minute. Let me see what's going on. Blah, 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 blah. Why does it feel that that is correct as well? I wonder why. Molecular formula of the major product. I think D must be wrong because of this word, major. How are you going to decide major versus minor? It's not like proceed via carbocation, right? I think A must be the correct answer there. Question 38. So we're looking for observation that is described correctly. So pentanal is aldehyde. So we have pentanal. So 1, 2, 3, 4, and 5. 5 carbon aldehyde. Phalanx reagents is blue in solution. It's got copper 2 plus aqueous. Of course, among other things, not just aqueous copper 2 plus. You will get orange red PPT. Your test for reducing sugar. Copper 1 oxide. It is copper plus 1 oxidation number. So A is already correct. I'm pretty sure A is already the answer there. And you don't change from green to orange. It's actually the other way around. Okay, it's actually orange to green. This is the chromium plus 6 in the Cr2O72 minus acidified. Going to chromium plus 3 in the chromium 3 plus, which is green in solution. So B is wrong. Pentane 2-on is a ketone. Ketone is not oxidized any further, not by Tollens, so you don't get any silver mirror. Ketone is not oxidized by Tollens any further. You have C6H14, which is going to be an alkane, and we know that alkane will not be further oxidized by KMnO4, so you don't do that because not alkene, CnH2n there, so only A is correct. Question 39, you're looking for correct statement. So we know that this is 4 carbon carboxylic acid. So this is what you call butanoic acid. When you form ester, you are not going to get propanoate. You can get something butanoate, but not propanoate. It must be 4 carbon from the acid side. They give you like the salt. That's why you name the alcohol before the salt name. They come from the acid. So A is definitely wrong. Empirical formula. Well, first of all, get the molecular formula. C4, 4 carbon. 7 plus 1 is 8 hydrogen. So H8O2. If this is the molecular formula, this is the actual number of atoms in one single molecule. I can see the simplest ratio, divide by 2 throughout. So 4 divided by 2 is 2. 8 divided by 2 is 4. 2 divided by 2 is 1. So what are you going to get? You're going to get C2H4O1. So empirical formula is the same as molecular formula. That is not true. I've just shown that it can be further simplified. Now what else? This is alcohol. So alcohol cannot be reduced any further. In fact, carboxylic acid cannot be reduced with sodium borohydride. You need LiAlH4 to reduce carboxylic acid all the way to primary alcohol. So C is definitely wrong as well. Now each of them will react with sodium metal. Sodium is a very reactive metal. You get alcohol. Alcohol will react with metal to give you the alkoxide, so C3H7O minus, and you get Na plus as a redox reaction here, and you get half H2 produced as a gas. So you will see this redox reaction very, very rapidly, obviously. And the other one will be C3H7 COOH, metal plus acid. You will get the sodium butanoate. This is called sodium butanoate. Just like if you use the butanoic acid to form ester, you will get something butanoic. Butanoate in the name of the ester as well. So what do we get? We will get hydrogen gas as well. So metal plus acid is a redox reaction. Metal plus water, metal plus alcohol is also a redox reaction. Hydrogen 0 there. And then you started out from the acid, where is hydrogen plus 1. You started out from this thing there. So sodium 0. Sodium in the salt is sodium plus 1. Sodium plus 1. Hydrogen in this alcohol, hydrogen in the compound has a plus 1 oxidation number there. So, D must be the correct answer. Question 40, the last question in this whole paper. So we have an infrared spectrum. The first thing we deal with infrared is to look for this particular region. So this one is pretty broad and strong absorption. We can be typically thinking about OH bond. Okay, OH bond is present. And we have this really strong and sharp absorption. I don't know, I could be wrong though here. This is not exactly 3000 to 3500 if you see the table provided in the question. So give or take, there's 2500 to 3000 as well. So this could be the OH, but this thing here around 1700. So this 1500, 1600, 1700. That is your usual region for carbonyl C double bond O around the 1700 region. So this is the C double bond O region here. Well, we're looking at what can be deduced. Well, it has C double bond O. That is true. That is of X, right? It consists of carbon, hydrogen, and oxygen only. It is X. It has C double bond O. If you have C double bond O, we're not talking about alkene. We're not talking about alcohol. So B and D are out. Is it a carboxylic acid or is it aldehyde or ketone? If it is a carboxylic acid, you can look at carboxyl OH. 2500 to 3000. 2500 to 3000, there is something there, around there for the OH, around there for the CO. If it is aldehyde or ketone, there is no OH carboxyl at all. So that means we are looking at carboxylic acid, which is most likely given that we have this absorption around the 2500 to 3000 wave number. So hopefully that makes sense there, that the answer there must be carboxylic acid and not aldehyde or ketone there. Okay, so this one was published in 2019 by Cambridge in preparation for the 2022 A-level chemistry curriculum, following a revamp of the syllabus slightly. And that's it really from me in this tutorial video. Thank you for watching. Don't forget to check out the many topical MCQs as well as topical structure playlists, and do consider upgrading to the silver tier, and you can enjoy a lot more yearly paper tutorials if you wish to. Otherwise, you are more than welcome to just use the free tutorials available on my channel. And I do appreciate the support. It is minimal cost. I tutor for $40 an hour, one-on-one. So do get in touch if you are interested. You'll be surprised at how much can be covered in 1 hour or 2 hour session with me, especially if you are a very strong student already and you just want to, get through stuff that you want to ask about specifically. Okay, thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry. That's at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected. Look forward to you joining my channel on the silver tier membership as well. Okay, see you in the next tutorial video.